Okay, now for the grand finale of these adventures in Lindblad land. So now in the next hour and a half, gonna deal with the last approximation that you need. So we did the two weak coupling approximations, Born, which is small correlations, Markov, which is short memory of the bath, although I've tried to show you that's a little bit more complicated than that, but it's also more interesting. And okay, at the end of these two approximations, we get this big equation, which I already rearranged in a way that looks more like the original Lindblad master equation with the commutator and the dissipator. Although this is written in interaction picture, so in Schrödinger picture there will be an Hamiltonian contribution here from the unperturbed dynamics. Now we know everything about these A's, we know everything about these gammas after the last two lectures. Now we're going to deal with a problem that I mentioned on the first one. That is, this equation is not CPT, is not a CPT dynamics, which means that rho of S can acquire negative eigenvalues during the dynamics. This is especially can be severe in the initial part of the dynamics, but there are simple recipes for curing this behavior, namely keeping the time dependency in these coefficients, but it can also happen at late times in the dynamics, and in some cases, you even get straight out the divergence of matrix elements. And for instance, one famous case is if you do this for an harmonic oscillator in a bath of harmonic oscillators. This is the Redfield equation, and basically, unless you're at a very high temperature or you introduce ad hoc terms to cure this behavior, you're going to get nonsense. So how to remove this problem? The standard prescription is known as rotating wave approximation, or RWA, or also secularization. And it starts by noticing that these terms, whenever you have different frequencies here. These are I recall these are the Bohr frequencies, so they are transition frequencies, and so yes, essentially, if you look at these kind of terms, these eigenoperators are causing different transitions, omega prime, between different pairs of eigenstates of the system, the unperturbed eigenstates. And of course, these guys, for instance, of course, this is a matrix. So these two transitions are changing both the bra and the cat inside of the density matrix. And you have these, these are so-called incoherent processes in the sense that they happened, they are purely dissipative and they just happen no matter what is the conservation of energy, for instance. Now, so if you keep all these processes all together, this is going to give you non-positive dynamics, and you see it just because essentially this is not in Lindblad form. This is basically the way you see it. If you want to see it in an example, it's more intricate and it's basically mostly numerical. It's very hard to see this analytically. But let's say the simplest fix is again rooted in a perturbative argument. So most of these terms have this oscillating prefactor in front, which this prefactor is essentially it's the unperturbed dynamics. So this comes from the interaction picture. So but of course there are these, whenever the two transitions are the same, which means that basically you're using the same jump operator on the left and on the right, these objects do not oscillate. So as a rough idea, at least the way it's usually presented, it's that when you actually judge the effect of these terms on the dynamics, the non-oscillating terms will have most influence because the others are essentially averaging out. Because I recall that the dynamics, the dissipatory dynamics, is generally slow, especially with respect to the unperturbed dynamics, which is given by this object. So basically, the RWA prescription is to drop all the terms that have these oscillating factors. So you keep only the diagonal elements. And if you do so, you arrive at an equation which is in Lindblad form. Yes, I'm gonna so if you do that, now I'm going back to Schrödinger picture. So I will show you the final result. This is the system, the Hamiltonian of the system. This is the dissipator. And then so I'm going to define the terms. This Hamiltonian contribution, it's a lamp shift. And this S and gamma are the real and imaginary part. I already wrote this at some point. So this is almost in the Lindblad form. The only step that's missing is to diagonalize this matrix and re-express this object in terms of the, it's essentially a rotation of this object. And so if you write down is it? I think so. Something like, it's a real and symmetric matrix usually, but okay. And then the dissipative part acquires exactly the Lindblad form I was using at the beginning. So this is just to, let's say, complete the story I began, and the jump operators are linear combinations. Sorry, there is also omega. They do depend on omega. So my insistence on analyzing the properties of the eigenoperators is because in the end, the jump operators are simply linear combinations of those. So the properties of this are reflecting the properties of this. So this is the confirmation that we Lindblad form, but there's only one ingredient missing. So the fact that we have to make sure that these rates are not negative. This can be shown. Essentially, you start using, it's called Bochner's theorem to judge, because this is essentially is related to the Fourier transform of the correlation functions, right? These gammas are, well, the Laplace transform, if you wish, of the correlation function. So it's basically the spectral density I was mentioning before. And you can prove that a matrix which is obtained in this way is actually a positive semi-definite matrix. So this is how you reach the final Lindblad form for the problem. Indeed, like in the example before, I actually shown that this gamma, in case of just one observable B, so there's only one index, there's no indices. I shown you that this was basically it's proportional to the spectral density, which is a positive function. So in that case, we had no problems about positivity. If you have, let's say, a mixed spectral density, the individual terms, so this is, yes, this is true, the individual terms might be negative, but then when you diagonalize it, you can prove that's actually positive. So this is how you derive the master equation in general. Do you have a question?
Yes. I heard this name before, rotating wave approximation. For example, in a Rabi mode or in a Dick mode,
Yes,
when you check out those terms that don't conserve the number of photons, things like this.
Yes.
I'm trying to make a parallel. I mean, when you do this approximation, there's kind of a conservation behind it, something like this.
No, the spirit is different. Okay, there are similarities, but there are differences. So I think, yes, the name of a rotating wave approximation comes from the rotating wave. And I think it comes really from the quantum optics community. So people were doing this at the Hamiltonian level, not on the Lindbladian. So the idea is, again, it's rotating perturbation theory. You have a reference dynamics, which you expect to dominate the physics. In this case, again, the unperturbed dynamics, the Hamiltonian dynamics, is the one that you take as reference. And these guys, the guys like this that oscillate the most are the ones that are more far from the unperturbed dynamics. So you have a reference dynamics, and you prune out whatever is too far from that. In that sense, the reference dynamics there you are invoking resonance essentially, because those are in quantum optics the most resonant. You keep the most resonant terms in the sense that they conserve energy. You destroy one excitation, you produce one photon, and vice versa. You don't destroy an excitation and a photon, despite those processes are present in reality. But on the basis of energy conservation, you discard them. I'm going to show you later that you can understand this more or less on those terms, but in a different language. There are a few nice papers written on these topics. In general, the Lindbladian version of RWA is more accurate than the Hamiltonian version. The Hamiltonian version is okay if you're doing weak coupling stuff, but if you are in a strongly coupled cavity, you should not make it, or you're going to introduce unphysical features into your problem. Okay. So I think I commented a lot on these jumps and stuff. One thing I haven't commented yet much is this object. So this is the lamp shift. So in principle, when you're coupling your system to a reservoir, the reservoir can also alter the coherent path of the dynamics. You get some modifications of the Hamiltonian of the system. Within the Lindblad approximation, these modifications are very benign because this object commutes with the Hamiltonian. You can have a glimpse of why if you recall that these objects are essentially behave as creation and annihilation operators for the system. So this removes an energy omega, and this adds it back. So if you start with an eigenstate, you are projecting to eigenstates an omega away, and then you go back. So this in general, let's say, if you have a non-degenerate eigenstate, the eigenstates will not be rotated among themselves. There is no modification of eigenstates. You just shift literally the frequencies of the transitions. So in this sense, this is a shift, a lamp shift. This is not true in this version. In red field, you do have couplings between different eigenstates, so you can actually change a little bit the coherent part of the dynamics. Here, unless you have degenerate subspaces, you don't alter the subspaces, the eigenstates. If you have degenerate subspaces, then you risk lifting the degeneracies, of course, because these guys are summed over degenerate subspaces. But again, usually people are not particularly interested in this because again, so while this object here, so the rates are local in frequency, so you just probe the spectrum of the system around a specific frequency, so you don't care, okay, if you maybe have a good model of the bath at low energy, but what happens at high energy, you don't care. This stuff is like a principal value integral, and so it will be sensitive to UV effects. So generally, since this is not altering the shape of the spectrum, you just assume that whatever spectrum you measure, it's the already renormalized one by the lamp shift. So, but in principle, you can compute it if you think you have a good model of the bath. Okay. So, what are the conditions for the validity of this approximation? As I said, the overall idea is that so rho s is decaying on some long time scale, which I called tau r, whereas those, at least when you see this in the interaction picture, where the fast path of the dynamics, which is the unperturbed one, is removed, this is slow, and then you have these oscillating factors, which evolve on a certain time scale, which is the inverse of the difference of the frequencies. Then this idea is that this oscillation must average out if they are sufficiently fast. In other words, again, tau r must be much bigger than tau s, or equivalently, omega minus the Bohr frequency differences must be much bigger than 1 over tau r. Before you, in case you're wondering what happens if omega equals omega prime, well, those are the terms we keep. Those are the terms that we keep, so we don't need to worry about those. So this only applies if this frequency difference is finite. If it's 0, then the corresponding term is automatically in Lindblad form, and you don't have to worry about that. At the beginning, I was giving as a condition for the Born and Markov approximations, that tau r was bigger than the correlation time of the bath, then okay, we had a more detailed discussion of Markovianity this morning, but let's say, roughly speaking, correlation time of we have these 3 timescales: correlation time in the bath, so dynamics, ampere-tube dynamics of the bath. Then there's this peculiar form of ampere-tube dynamics of the system, and both must be much smaller than the interaction, let's say the decay rate induced by the interaction. There is no obvious relationship between the two. They could be one bigger than the other. So again, this is at least for me, it was a little bit bizarre, this formulation, in the sense that here we are not, it's not these omegas are not the energies of the system, are transition frequencies. So like different transitions, and you are comparing the transition frequencies. So if you wish, I think a good way of visualizing this is to imagine that we can measure the spectrum of the excitations emitted by the system. Think of an atom that's decaying or a molecule that's decaying, and you measure the spectrum of the photons that come out. In this formalism, of course, we are integrating out the bath, so we don't know what happened. But in many cases, essentially, if you have a transition at a certain frequency omega, you will see a peak at the frequency of the transition with a certain width, which is this tau r to the -1, or decay rate. So this condition is equivalent to say that we have 2 transitions, omega and omega prime, and we can perform the RWA if we can resolve the 2 spectral lines, which means that if the distance between the 2 is larger, much larger than their width, which is again, gamma. Could be gamma 1 and gamma 2, but that's either of the 2 essentially works. You took you can take the bigger of the one, the bigger of the 2, or the sum. The difference is irrelevant for this. So the whole idea is then that if these 2 processes happen with different frequencies, and the frequencies are sufficiently defined in the sense that these processes don't overlap, so the uncertainty of the energy on one process is not overlapping with the uncertainty of the energy of the other process, then we can consider these processes are as happening independently of each other, because that's what the RWA is telling you. In principle, all these processes with omega and omega prime in the Redfield equation, they are all coupled. Of course, if there are selection rules, which there are often, they are hidden in the structure of these matrices. But in principle, right, you can have a transition at omega and omega prime, and there's nothing that's preventing them from interfering with each other. But when you do the RWA, you are assuming that all the transitions which are too detuned from each other, they just happen independently. So there is no need to keep track of the coherence between them. Vice versa, if the 2 transitions are degenerate, well, that's not a problem. This is automatically Lindblad. So if really the 2 transitions are on top of each other, and then let's say there will be coherence, and in this case, coherence, it means this. If you imagine you have 2 degenerate energy level that both go to a third one, coherence means that the Lindblad-Master equation is able to see interference between the 2 processes. So in this sense, coherence, because but these terms are automatically taken care of because they happen at the same frequency, and in this sense, this thing works automatically. The dangerous regime, which is the regime in which RWA cannot be applied, at least not in this form, is the intermediate one. you have two spectral lines or two transitions which cannot be resolved, but they are not coinciding. So the two frequencies are different, but the distance is of order of the decay rate. So if you have transitions which can happen in this way, then RWA cannot be applied, in the sense that if you do apply it, you're going to lose the fact that these two transitions do not happen independently of each other. They can still interfere. And again, the typical example is a lambda system with two slightly displaced energy levels that emit into the same level. And these two processes can still interfere. Of course, if the interaction is enough that you have a broadening which is sufficiently large. If you have the interaction which is so weak that these lines are very sharp, then you're back to this situation. So I'm going to comment more about this. But let's say this is the rough, well, a semi-quantitative, not even that rough, it's semi-quantitative way of ascertaining if RWA can be applied. What happens if you cannot apply? Well, there's a huge literature on that, because this is I think it's the most debated of the assumptions under the Lindblad equation, underlying the Lindblad equation. And there's basically an industry of people trying to derive master equations which do not employ this approximation. Because in the sense you are throwing away lots of processes. All these processes with omega different from omega prime are just thrown away, which is a draconian solution to the problem of keeping this thing positive. You have too many processes that tamper with positivity, you just remove them. Most of the cases is innocuous, especially for like atoms and small molecules. There are relevant cases in which this cannot be done. And then, well, there are modifications. Either you stick with Redfield and hope you don't get negative eigenvalues, which is an approach which is actually usually very viable, or you try to do partial stuff. I mean, I can mention them later, but I don't want to. I don't think that's worth entering into details. Also because my knowledge here is limited, because the amount of stuff that people have tried to do this in this regime is infinite. But yeah, let's say at the simplest level, in general, you would like to stick with Redfield in case of if you have these transitions which cannot be resolved are the focus of the dynamics of your system. So I can give you a slightly better account of this approximation on the lines of the rotating wave approximation that you do in quantum optics. Let's see. So this is essentially a dynamical view, in the sense that you have some dynamics, and you have a slow part and a fast part, at least in this reference frame, which is the one of interaction picture, and you are invoking the intuition that oscillating stuff should average out. And by the way, I mean, most of the things I've discussed in these lectures is basically exactly a matter of timescales. You have a fast timescale, a slow timescales, and then you can make approximations. Now, you may, I don't know, if you feel comfortable with this explanation, which is very hand-waving on, oscillating stuff, well, how does this averaging actually works out in practice? A different version is a more of a static version. We start from the Schrödinger picture. So we keep the fast part of the dynamics. And then those oscillating prefactors are actually going to be this part here. It's just a free evolution. I'm not going to, write down everything, because it's mostly qualitative. But I'm going to mention one thing. Okay. Sorry. If I go to the Schrödinger picture, I'm going to have this commutator part, which is the unitary dynamics, and then I'm going to have the dissipative part. And I'm thinking that now I'm back to Redfield here. So I have all this complicated mess. I won't write it again. And then I'm going to, well, I'll erase the. So I'm going to take matrix elements, as usual. And I'm going to work in the basis of eigenstates of the Hamiltonian, as we've done throughout the lectures. And then we have stuff. Essentially, okay. So in general, the outcome is something like this. So it's, as I said, Redfield and Lindblad are both linear ordinary differential equations. And we just know that essentially this big matrix has a specific contribution coming from the Hamiltonian. And we can say, let's say, in this picture, the distinctive feature of the, let's say, of the Lindbladian part of this Redfield equation is in the fact that not all, let's say, not all the elements of the density matrix are coupled together. So there is a degree of sparsity, of sparseness in this matrix. And the distinctive feature is that essentially the populations are coupled only to populations. Whereas, so this is Lindblad. Whereas coherences are coupled only with coherences. This is essentially the way you see the Lindblad. This is the feature of the Lindblad dynamics that identifies it against Redfield dynamics, in which instead you have in principle all possible couplings. Populations with coherences, coherence with populations, and all together. So to see this essentially is the same reasoning I was doing here. In the Lindblad part, you have the eigenoperators which have the same frequency. So essentially, if you components, I mean, let's say, trivially, make an example. Suppose that my rho S has some component, has some diagonal component, okay, with some weight, okay? I'm ignoring the rest for now. Now we have a term like this. Now these operators are something like a projector, where, of course, I'm assuming that there is a single non-degenerate level with energy differing from the original energy by omega. Because, of course, the omegas are exactly the set of allowed transition frequencies. So this is just transfer you exactly from an eigenstate to the other. Now, if you compute this term on this object, you just get M. And this is another population. So the Lindblad part is only, at least, let's say, when you don't have degeneracies, is coupling populations with populations. And by the same reasoning, you can see that it's also coupling coherences to coherences, never coherences to population. Coherence means you're going to have two different states, but then this will give you to M and to M prime. Same reasoning. So from this perspective, RWA means that you take this big matrix that you get from Redfield, in which all the couplings are allowed, and you erase part of the couplings based on this criterion. So in more detail, so this, let's say, is the generic structure of the Redfield equation in the basis of eigenstate of the Hamiltonian. So all couplings are in principle allowed. Now, RWA, it means that we take the couplings between populations and coherences, which are this, and we remove them. And analogously, we take the couplings between coherences and populations, and we remove them. Also, technically speaking, we also need to, again, using the fact that this object transfers the same energy from the right and from the left, the same energy omega, you can basically convince yourself that you just take this bit and you have also to impose that the omega m n is resonant with omega pq. But okay. This is, let's say, for completeness. So you also prune a little bit of this stuff. Does this make sense to you? Maybe. So yes, his question is why there's an index, a discrete index A, and then a sum over frequencies omega. Well, usually when you write, the obvious answer is when you just see it written down like sum over the sites of operators acting on the sites is basically wrong. You are approximating too much. Again, this stuff is essential if you have some structure in the, sure.
I think Victor is right. Perhaps I should repeat the question broadly. So I was asking a question that maybe some of you have in mind. I mean, I have an answer, but I think it's important for all of you. So like he says that the arrival point is sum over A and omega in this last dissipator that he has written. Can you point it out?
Yes.
So this is the arrival point, right? So looks like everything is all right. But when you write down the dissipator, in any case, you have only one sum. For instance, you have losses on a spin chain, and you sum over I, sigma I minuses in the dissipator. So it looks like that in all the cases when we write down the dissipator, there is no sum over omega. And I was wondering whether you could clarify this point. Do you see the issue, folks? Right? Everybody that writes a Lindblad equation, at best, writes only one sum. At most, writes two sum, but they are sum on two different spatial indices when you have correlated losses or correlated noise. But there is never this sum over capital omega. And so I was wondering why Martino considered this a good point to stop.
Well, so I would say at best, okay, the presence of more than one omega, of course, is the condition for having more than one omega here. So if you have a collection of two-level systems which are identical, of course, naturally, you just have one transition frequency. So in that case, it's very natural to not having this sum over omega. But if you have a more complicated system with maybe interacting parts, these levels are going to be, let's say, more than one necessarily. So you do have an extended sum. I mean, you can consider this A omega as a composite index, and you just have to enlarge this sum to a single sum of a composite object, of course. But as I was already telling you repeatedly, like I don't know, A might be on a position because it's equivalent to the original indices, which might be a position, but then these objects are no local objects. The omegas, well, again, also in that case, it depends. If you have some information on the on the reservoir, it might be that, for instance, the dependence on omega of gamma is very mild because the spectral function is very flat in the region of spectrum that you're interested in, so that you basically forget about the existence of this, at least in omega. This could be an option, or maybe some omegas are very big and the corresponding decay rates are very big, so those processes are going to be erased very soon from the dynamics, and only the slowest decaying ones are the interesting if you're interested in long-time dynamics. I'm guessing, possible correct way of handling this instead of just writing everything as if it was a local interaction when it's in fact it's not.
Now, in fact, the answer I would have given, now it's a real question. The answer I would have given was that, as you said, exactly at the beginning, typically we write down what? Bosons and spins, that's it, or fermions. And the coupling with the system and the bath is the typical FF dagger or stuff like that. So as you said, you're going to have only one omega because you just flip down, up, or you create or annihilate. They are all equally spaced. That's the 99% of cases. That's the answer I would have given. You are saying I should be worried also about the nature of the buff. Now it's a real question. So you are imagining a case of a spin chain, just to fix ideas, where you have an innocent coupling to the buff, like sigma plus A plus emission conjugate. Where the buff is crazy, I should be worried about the sums over capital omega. I'm really
Well,
asking.
sure. If the bath has a frequency structure, so that it's not like something very flat and without. So the Markovian, okay, if the bath is doing crazy stuff, it's not Markovian.
We are not there, right? We will never get there.
But if you have some dependence on the frequency, but even like, as I said, for the electromagnetic field, the spectral density goes as the frequency to the third. So like if you have two transitions and one is bigger than energy bigger than the other, the corresponding gammas might have a sizable difference in size. A factor of 2 translates to a factor of 8, so there's an order of magnitude difference. So in that cases, if you have more than one transition that is that's available, then the two gammas are going to be widely different. And in principle, you should also keep the omega in the jump operators.
Okay.
Again, this is all like for thermodynamic consistency of the situation. again, this is, the whole purpose of this is that you somehow have an actual system and you have a model of the reservoir which you are confident enough, and you want to do something that could stay on top of experiment. Now, if your goal is just to have an idea of what dissipation is doing on some system, you can use this in some way at a phenomenological level. You say, oh, well, these are the things that are going. These gammas are going to be some numbers that you fit to experiment, and you will probably have results that might be in qualitative agreement, because this, after all, this is really giving you dissipation. So non-unitary dynamics is embodied by this object, no matter what are these objects here. You're going to always broaden your peaks and see loss of particles or dephasing, erase coherences. So you're going to see all of that. Of course, if you end up in a state, if you start with if you remind a system which is coupled to an environment at thermal equilibrium, and you get a final state which is not in thermal equilibrium, then it's for sure this thing is not, is not realistic. But it might be made realistic by breaking the condition of equilibrium in the environment. If you have crazy drives and maybe multiple environments at different temperature, you can, play a lot of games. But it's a matter of, what is your goal in using this equation? If you want to be really careful about the physical implementation, this is the way. You need to care about all these indices and the structure of the transition in the system. If you have more than one transition energy, no. That's the thing he was saying. You still need to. So maybe it's easier. Let's say, suppose that I just have one B operator. So there is no sum on A, because there is no matrix structure. These are just numbers, right? Right. These B operators. So you forget about that. But if you have a composite system, which is not a two-level system, which only has one transition, but if you have a ladder of transitions, then each transition will have its own jump operators depending on the frequency, and its own for each frequency. Yes. Yeah, this is, let's say, this is in full generality. If you have more than one coupling, then you have also to worry about this stuff. Okay. Coming back to this rotating wave approximation. So this is, let's say, this is not super obvious. I mean, took me some thinking to get to this structure. But it's known. It's like I didn't invent this, but it's, let's say, an alternative phrasing of the rotating wave approximation, which you can only have if you just sit down and look at the structure of the equations that you have, at least in this basis of eigenstates of the Hamiltonian. Actually, the fact that the Lindblad master equation gives you in the Lindblad master equation, the evolution of the population is decoupled from the evolution of the coherences is a very well-known fact. And this equation here, the equation for population, is a classical rate equation. So you can write it down in the usual. I don't know if you ever seen classical Markovian processes. It's okay. All these rho mm are probabilities, right? Because they are eigenvalues of a density matrix, so they are positive and sum to 1. And so this equation is something like the rate the rate of loss from a given level plus the rate of gain from other levels. I don't know if you've ever seen an equation like that in your courses. So this is a classical Markovian process. And if you work out these coefficients, which are these gamma rates, which are basically those gammas, if you work out these coefficients, you will see that they are exactly defining a classical Markovian process. So they sum to 0 so that the probability is conserved, and they're positive. This is the original master equation, but and you find it as a specific subset of equations that you get from Lindblad. This version here, let's say from density matrix, is even a name as a Pauli master equation. But of course, it's the original master equation. And as a bonus for quantum systems, you also have the equation for the coherences. Actually, if all transitions are non-degenerate, so all the lines of the spectrum are different and distinct, then actually these are not even coupled equations. Each coherence evolves on its own. Because here I'm summing over all the coherences which have the same energy splitting. If you don't have, then this is just some coefficient. This, which is of course a negative coefficient because you get decay. So this, let's say the magic of Lindblad that gives you a positive semi-definite dynamics emerges because there is this actual structure in the matrix. You get a classical rate equation for the populations, and the coherences evolve on their own. From this perspective, the question, what is the condition of validity of RWA, can be answered in a more detailed fashion. Again, I'm going to use, let's say, a toy model, which is not as complicated as the previous one. It's also very less spectacular because it's a very silly model, and but it gives you an idea, especially on how the condition of this object actually emerges, except for, beyond this hand-waving stuff about oscillatory factors. So let's take let's take this equation, which is really a caricature of that equation. I'm taking essentially one population, which is coupled to one coherence. And these coefficients are these big coefficients here. I'm dropping a little bit of indices, and I'm also assuming that these two objects are complex conjugate of each other, so that this is essentially a dynamics which is given by a Hermitian matrix. This is generally not the case. This matrix is not Hermitian. But OK, it's a technical complication that doesn't alter the conclusions. Also, I mean, this is completely realistic. You need at least 3 equations to have a consistent master equation, because you have to have the two populations, and, well, in principle, 2 coherences, but maybe just one because they're actually complex conjugate of each other. But, this is the bare minimum for doing anything meaningful. So, we have a linear equation. Again, we know its solution. We just need to diagonalize this, and this is where the assumption of an emission matrix comes into help because it's easy to diagonalize it, but you can do also with a non-Hermitian matrix. And so in this picture, this condition of RWA means that we just erase the off-diagonal elements. The population cannot be coupled to a coherence and vice versa. So in RWA, we are just keeping this. Of course, we know what is the dynamics of a diagonal matrix. So yes, you're going to have a vector. Let me use a vector notation for this object. OK. Which is, of course, the, well, ah. So this is the RWA solution. But now we have also the full dynamics without any RWA. It's diagonalizing a 2x2 matrices, 2x2 matrix. I won't do that because, well, you can do that if you wish, but there is no point in computing the exact values. But the whole idea is that you need to find you're going to find 2 eigenvalues and 2 eigenvectors. I call them lambdas. Yes. So these are the eigenvectors of this matrix, which will depend on G, and these are the eigenvalues and depend on G. And so the quantitative, we can ask a quantitative condition. What is under which circumstances this dynamics looks like this? It means under which circumstances the eigenspectrum of this matrix looks like this. Well, obviously, the condition is perturbation theory must be valid. So the difference between the spectrum structure of these two must be small. And actually, here you can use the usual time-independent perturbation theory that we know from our quantum mechanics courses, and find that they're essentially 2. And I'm going to write like this. So there's level repulsion plus other term. And these corrections are like corrections to the ground state of a quantum system, which are quadratic, because, of course, the perturbation is completely off diagonal. And this delta omega is, well, the difference of the diagonal elements. Exactly like in quantum mechanics, you get difference of eigenvalues here. And the same, these two V's are going to be 1, 0, and 0, 1, which are the eigenstates of the diagonal matrix, plus a correction of order G over delta omega. And so we can give a quantitative answer to the question I was asking before. These objects must be small. This G in modulus must be much smaller than this. This is the condition, really the condition for being able to apply perturbation theory to this matrix in terms of G. Now, if you retrace, let's say, if you sit down and start checking matrix elements of the Redfield matrix, you will see that R1 is essentially one of these gamma objects. So I mean, something small. Whereas R12 is the one that contains the dynamics of a coherence. And at least even disregarding interaction with the bath, coherences do evolve. They acquire a phase. So this is essentially I omega, okay, omega 1, 2 between the two levels. So this is a Bohr frequency. And again, similarly, this G object is something of, well, it's basically gamma. It's the decay rate that is associated with this. Again, this is, you need to sit down and start taking matrix elements, but you can convince yourself that this is true. So if you put everything together, you are getting that, yes. So this is tau r to the -1. So all in all, tau r much bigger than 1, which is the condition I wrote before. So we recover in another fashion how, I mean, this argument about oscillating factors, which in this sense is really, it can be rephrased as the condition of validity of perturbation theory for a certain big matrix that you get from Redfield. And if you wish, you can be more quantitative and do the full theory. There are people that did this to assess the kind of problems that you have. The advantage of this, I mean, even this toy model does show something interesting in the sense that you can also say something about the kind of errors that you get, so the kind of terms that you're missing. So take these terms. We have terms which are like this. We can expand. Let's say I take the +1. We can expand. You have G over delta omega. And then, wait, I'm gonna write here, sorry. So I'm taking this bit here. So this is the unperturbed eigenvector, which is the only one that you keep in Lindblad, plus the Redfield correction times R11 T minus, no, plus G square delta omega T plus higher order terms. So whenever you do the RWA, you are throwing out this and this, which means that this is a kind of, I don't know, systematic error. You're losing a fixed, you're losing something that has a fixed behavior in time. And here instead, you are measuring a slightly wrong frequency or decay rate. So this object is guaranteed to be very always smaller than this because we are assuming that perturbation theory holds. So the deviation of the lambda plus eigenvalue from the Lindblad one is small by definition. So there's no like secularity. This thing will never blow up in time. But this, I mean, it's an oscillating factor, and you can get a phase lag at some point. But of course, this only happens on timescales at which this term becomes of order 1. So when when the time is sufficient to make this extra phase or extra decay be relevant. And if you rework out the various factors, this means that the time scale. What am I writing? Yes. So this time scale, at which essentially RWA breaks down in the sense that even the small error that you make, you're going to start seeing it, which is delta omega over g squared. Now I said that g is basically the inverse of the relaxation time. So this is delta omega tau r times tau r. So whenever RWA is a good approximation, this is a big number. So you start feeling the difference between RWA, the Lindblad dynamics and Redfield dynamics, or the true dynamics, only after a few relaxation times. But at that point, your dynamics is already over. So at least, let's say, this approximation is self-consistent. You're not throwing away stuff that you should keep. So this is reassuring, at least. Okay. I'm going to give you a few examples. So not like maybe detailed as the ones before. The point is, in which scenarios do we expect this approximation to break down? What are the conditions that you should have to look for? So the main thing that should ring a bell whenever you see it is if you have almost degenerate spectra. So if you have transitions which are closely spaced in frequency. In the analogy with spectra, if you have spectral lines that start to overlap, this is a sign that probably you cannot use Lindblad, at least not in this form. You need to do something beyond Lindblad, maybe Redfield, maybe modified version of RWA. It's a matter of taste at that point. So in which cases can we expect this kind of stuff? Well, if you have the typical systems used in quantum optics, meaning atoms in cavities or this kind of stuff, this is rarely the case, especially atomic transitions. I mean, every time you have a discrete spectrum, let's say the fact that two transitions have an almost matching frequency is fine-tuning. Generally, you have a system and the transitions are going to be different, or exactly coinciding if there's a symmetry that's enforcing that. So in atoms, this is almost never the case. Also because atoms are very weakly coupled to the electromagnetic field, so the lines are always very sharp. And I'm thinking about, since we have an experimentalist, I'm thinking about intrinsic lines, not the Doppler effect, not thermal broadening, the intrinsic ones. What can happen is, a situation which might be troublesome if you have a degeneracy which is lifted by a perturbation. In this case, it's actually natural that you have lines that are very close to each other. For instance, you apply a very weak magnetic field and you split a Zeeman multiplet. Now, in this case, depending on the magnetic field, you could, in principle, always find a magnetic field which is small enough to have this problem. This thing seems to be known, but usually it's not a problem, again, because even with magnetic fields, the intrinsic line width is very small. That's as far as I understand, so it's almost never the problem. Although there are proposals to measure these kind of processes with atoms, exactly tuning the magnetic field to have this situation. Yes. Then, when you have discrete systems, you might have, like the case of atoms, usually you have a few low-lying levels, and then the levels get denser and denser until you reach the continuum. Now, if you have a continuity of energy levels, that condition is the norm, of course. You can always find, unless you have a specific selection rules that forbid some closely almost the generous transition to happen at the same time, you expect the norm. So transition to the continuums, you cannot work in RWA, you cannot work with Lindblad. At best, you can work with Redfield. You might be worried maybe transition involving Rydberg states, because are very closely spaced. So the level spacing here goes down as a third power of the principal quantum numbers, or principal quantum number. But in this case, at least for simple atoms, it seems that like there is a saving mechanism that prevents RWA from breaking down, and it's the fact that the this state also become yes. What am I saying? Yes, also become very long-lived. So the lifetime grows as a power of the principal quantum number, which is between 3 and 5, depending on the angular momentum. But overall, if you multiply this, you don't get something that goes to 0. You get something that either stays more or less the same, or it's even growing. So even for transition involving Rydberg states, this is safe. But again, the idea is whenever you have this situation, you should be worried about checking that everything else works. The simple fact that you have a priori two closely spaced transitions doesn't mean that RWA breaks down necessarily. You have to account for selection rules, and you have to account for this kind of stuff. If the coupling is sufficiently weak, then you might have a very long lifetime. So even if this difference, the timescale difference of the two frequencies is very long, this is even longer, so it's safe. At least for atoms, there is one case in which the opposite happens. If you start exciting core electrons, so use X-rays, then the dominant transition path goes through emission of electrons. So this is no longer an atom de-exciting by emitting photons, but it's an atom de-exciting emitting electrons. And then the interaction that causes the emission is the Coulomb interaction. And this is big. And so you have an extremely short lifetime. And then indeed for core spectroscopy, this is the norm. It's very hard to resolve the lines. So they're always mixed together. Okay, this is essentially for finite dimensional systems. If you go to system with a large Hilbert space, then the trouble becomes the norm. Trivially, if you have a free particle immersed in a bath, it's a quantum random walk. The spectrum of a free particle is continuous. So RWA cannot be applied, and this is very well known. Indeed, you will find master equations for quantum random walk, and if you look at the derivation, it's not Lindblad. It's actually Redfield, and people actually put a little bit ad hoc contribution to make the Redfield equation in the Lindblad form. So again, you get positive dynamics. But for instance, you cannot derive it in this way, because RWA is going to break down. Or in principle, I mean, there's always, when you have very small level spacing, there's always a risk that Markov breaks down, because you start probing the spectral function of the bath close to the bottom when there's the non-analytic point. So in system with a continuous spectrum, this is always more sketchy. And a prime examples of systems with a very closely spaced spectrum is many-body systems, of course. If the parts of the system interact, like in integral model, the level spacing goes down algebraically as the number of particles increases. In an integrable model, this goes down exponentially. I mean, the outcome is the same. In these systems, small energy spacing, level spacing is the norm. So RWA is probably going to fail. And this is the second part of the answer that to a question that you did yesterday about many-body systems. When your system is many-body, you risk breaking down Markov because of the edge effects. And also, the RWA is almost guaranteed that you fail for this reason. Because essentially, I mean, delta omega is going to go to 0, whereas the time scale of the decay is finite because it doesn't care about the level spacing. You just care about the frequencies, not the frequency differences. So that is the norm. Unless, again, you might have something that saves you. For me, a nice example is suppose you have an Hamiltonian, which is just free particles. They can be electrons, sorry, they can be fermions, bosons. It's for what I want to say, it's irrelevant. I'm going to assume they have just one particle, but with a almost continuous spectrum. You think, okay, it's a big box. There is some quantization condition, and these momenta are something like 2 pi length of the system times some integer, right? So they're closely spaced if the size is big enough. So if you look at energy, you're going to have something like this, okay? I'm going to make a very simplified assumption that there's a one-to-one correspondence between energy and momentum. This is generally not the case, but the result is the same, and it's easier to understand it like that. It can be gapless, it can be gapped. Again, this is not important. Suppose that you derive your master equation, and what is happening is that the jump operators are removing particles. So you have jump operators, which are something like CP. And of course, it makes sense that they act in momentum space because they know about thermalization. Now, in principle, you derive your Redfield master equation, and you have this kind of terms with, in principle, 2 different energies. So are going to be something like because these are the energies available, right? This is initial energy, which is epsilon p, minus final energy, which is 0, because I'm removing the particle. And these energies could, in principle, be different before doing the RWA. And, of course, you can always find 2 energy. I mean, this is a continuous spectrum. You can always find 2 transitions which are arbitrarily closed in energy, right? The momenta are essentially continuous, so you can always have two of them spaced together. So it would seem like you cannot do this game anymore. But here comes a selection rule. If you assume that there is translation invariance, and I'm assuming also that the couplings are not doing anything bizarre in that regard, the coupling with the bath. Now, the dynamics must be translation invariant, so it must conserve momentum. So these transitions with different momenta are not allowed, because if, for instance, my initial state is this, during the dynamics, this state can only generate other diagonal components. So if you, when you have a symmetry in the Lindblad master equation, it means that you take these big matrices and you look at them, you will find that they are block diagonal and labeled by momentum space. So if this is a so-called weak symmetry, then your master equation, whether Lindblad or not, must conserve this structure. So if you have diagonal terms must be mapped to diagonal terms. But this can only happen if the two energies are the same, or the two momenta. So I'm assuming that the two momenta must be the same, so the two energies must be the same. So this actually works if you try to do it in practice. You couple your favorite model with a bath of, I don't know, harmonic oscillators in a way that's translation invariant. And if you do all the sums, essentially if you work out all these alpha and beta coefficients, the structure of the matrices, you will find that all terms which do not conserve momentum cancel out, but this ends up imposing conservation of energy in the sense that the two energies must be the same. But if the two energies must be the same, then this is already in Lindblad form. The system has done RWA for you. So there are escape routes from this. This is a somewhat special situation which happens when you just have one energy involved, so you're just removing or adding particles from the system, and you have translation invariance. If, for instance, the dissipation is just moving particles from one momentum to the other, then this won't work anymore. So these were the transitions. Another possibility is that you have transitions of this kind from one momentum to the other. And then this term is going to look something like this. So you map P and K to P prime and K prime. Now this still, you might like to impose momentum conservation, which, well, looks like momentum conservation. The sum of this and this must be equal to this and this. But momentum conservation in this case does not imply that the energy exchange is the same, unless you have a strictly linear version. But you know, if you're maybe working with a topological insulator with chiral edge modes, then this might be the case. But otherwise, these two energies are unrelated. And in this case, RWA cannot be applied. You cannot expect to work. So either you stick with Redfield or you choose an entirely different kind of dynamics. What else? I think so. Yes. No, I think, no. Well, I think that this was more or less everything that there is to say, or at least everything that that it's in the review. Extra questions? Besides the fact that you want to maybe take a nap?
So a student may ask, every time we add a Lindbladian to a many-body system, it's just wrong description, so all papers are wrong.
My honest answer at this point
On
is
record, so.
yes, my honest answer in this answer is probably yes. When you're, I think the only case in which I know it's kind of safe is exactly this one, in which you're like, suppose you have like, I don't know, free fermions or free bosonal lattice, and you just have particle removal on each site. Then this maps exactly to this situation here. But otherwise, I don't know, like, there are people that did the exact dynamics, especially with free systems, and compare with Lindblad. And it seems that in the end, often, somehow this thing works out in a decent way. But to the best of my knowledge, there are like no general results about many-body systems coupled to environments, whether this machinery works or not. I would say whenever people write down many-body systems with dissipation, it's at best a phenomenological choice. It doesn't mean that has the right properties, but I mean, for me, it's hard to say a priori that's supposed to work and it will just, be one-to-one correspondence with experiments. I would expect the opposite, actually. But that's, I mean, that's for you and us, and you and me to discover, I guess, if we are curious, curious enough. Yes. So this is just to, make our colleagues around the world happy. That we're dissing their papers on many body dissipation. Yeah, sure. Well, thank you for listening.